Hi students, welcome to video on square wave generation. Uh, we will understand the working of the square wave generation, and we will also conduct an experiment using operational amplifier how to generate the square wave generation, square wave waveforms. We all know that op-amp can be used as a comparator. So now I have written the op-amp symbol. Of course, we all know that op-amp needs a dual power supply plus VCC minus VCC. Suppose if I consider an op-amp which is mu A741. So let me identify the pin numbers of inverting terminal, which is pin number 2, the non-inverting terminal is pin number 3, and the plus supply is pin number 7, the negative power supply is pin number 4, which will be connecting to 4, and the output is at pin number 6. And we know the theory of this operation amplifier in open loop condition. So V naught will be plus Vsat, V naught will be plus saturation voltage. If the voltage at the non-inverting terminal, which is pin number 3 here, if it is greater than the voltage at the inverting terminal. And the same output voltage at pin number 6 V naught will be minus saturation voltage when the voltage at the inverting terminal is more than the voltage at the non-inverting terminal. So this is the basic we should know in order to understand this square wave generation. Now let us see how do we use this property of the operational amplifier. Of course, why it is so means because we know the expression for the output voltage of an op amp in open loop condition. V naught is given by the open loop gain times the voltage at the non-inverting terminal minus the voltage at the inverting terminal. As A naught is a pretty large quantity, maybe in the order of 10 power 4 or 10 power 5, whatever the difference that we get, that will be multiplied by this huge number. So that will end up with a very large voltage, which is not possible to get from this. So that's why the output voltage will either settle at plus Vsat or minus Vsat. So that's what is the theory. We already know about it. So what we'll do is, so we will take up this operational amplifier. We'll take up this operational amplifier, and then, so this is minus plus, and let me provide a positive feedback to this. So now when I say positive feedback, a sample of the output voltage is fed back to the input, which is, okay, now if I consider this as R1 and R2, if I ground this, so if I say this is voltage at the non-inverting terminal, so voltage at the non-inverting terminal V plus is nothing but V naught into R2 by R1 plus R2, R1 plus R2. So depending on the values of R1 and R2, the V plus, the voltage at the non-inverting terminal, which is this, will be always a fraction of the output voltage V naught, the fraction of the output voltage V naught. Now, so let me consider this is my inverting terminal, which is, okay, suppose if I try to identify the pin numbers, of course this will be connected to a supply voltage which is plus 5 volt, and this will be connected to minus 5 volt. Of course, it is also possible to connect to plus 12 volt and minus 12 volt, or minus 10 volt plus 10 volts. So it can be any voltage. So since I'm conducting the experiment using analog discovery, so I'm connecting it to plus 5 and minus 5. This is pin number 7. This is pin number 4. This is pin number 4, and pin number 6 is the output. Pin number 3 is the non-inverting terminal. Pin number 2 is the inverting terminal. Suppose assume that the output voltage is at plus 5 volt. So assume that it's at plus Vsat. So we also know that the saturation voltages are always less than the voltages that is the supply voltage. So let me consider, so let the positive voltage be, so let me just consider a typical value that we usually get it using the experiment. So we let us assume that the positive plus VSAT is around 4 point, which I'm just measuring using one of my reading, of course, which you are seeing. So this is my okay, we'll just come to this in detail later. So this is my plus voltage, which is C2 maximum is 4.1 volt, and minus VSAT in this particular case is minus VSAT is, suppose if I just come here, it is minus 2.74 volts. This is the supply voltage. Okay, fine. So this is what the typical voltages I am having. So let the output voltage be at plus VSAT. So let us assume that this is at 4.1 volt. Let us assume that this is at 4.1 volt. So let me use R1 as 1.5 kilo ohm, and let me assume this R2 as 1.5 kilo ohms. Suppose if I ground this, so what I'll do, I'll simply ground this. So this is always at 0 volt. When this is at 0 volt, and what is the voltage you have here? So this is 1.5. If I substitute this as 4.1 volt multiplied by 1.5 by 3, so this is naturally half of this 4.1, which is 2.05 volt is the voltage at the non-inverting terminal. So now supposing that this is the connection I have made. So if I make this as the connection, my output voltage is always 4.1 volt, because this is 0, this is 2.05 volt. So is this condition satisfied? So voltage at the inverting terminal is 0 volt, the voltage at the non-inverting terminal is 2.05. So how you got this as 2.05 is because you are taking a you're using a potential divider R1 R2 to divide this output voltage, which is assumed to be at 4.1 volt. So the voltage at this point is now half of that, because you are dividing it using two equal value resistors. So if this is not changed, the output voltage is always at 4.1 volt. So this is not the requirement. What I want to have is I want to generate a square wave. So let us slightly modify this circuit. So what I'll do is I will take out this from ground. I just take out this from ground. So let me connect. So let me just take out this. Let me connect a capacitor now. So I will connect a capacitor. So this is my capacitor. So now I have taken out the ground. I have connected a capacitor C. Let us assume that this value of capacitance is 0.1 microfarad. So I have connected a capacitor. This is no more connected to ground. Pin number 2 is connected through a capacitor to ground. So when I make this, so now let us assume that the voltage across the capacitor is initially 0 volt. So this is also 0 volt, meaning the output voltage remains to be at 4.1 volt. So when this remains to be at 4.1 volt, because this is 0 and this is 2.05, so this condition is always satisfied. So this continues to be at 4.1 volt. So now, so let me just consider that condition where, so this is with respect to time. So this is my capacitor voltage. Let me say this as 0 volt, and let me say this is, okay, let me say this is my V0. So V0 is at 4.1 volt. So this is at 4.1 volt. So what is at V plus? So at V plus, you have how much? You have a voltage which is 2.05 volt. So what is the voltage at this inverting terminal? So let me write that also. So let me write that. So this is the voltage at V minus, which is 0 now. So this is 0. So this voltage is 4.1, this voltage is 2.05, and this voltage is 0 volt. Suppose if this continues to be there at 0, because this continues to be at 0 because there is no charging path for this. There is no charging path for this. So this continues to be at 0. So this is continuing to be at 2.05. So this continues to be at 4.1. So let us now assume that, let me introduce a path for this capacitor to charge. So let me provide some charging path for this. So let me say this is my RT. So I have connected the resistor RT to my output voltage point, which is pin number 6. Now this is in turn connected to pin number 2. So now this capacitor has got a connection to this pin number 6, which is at 4.1 volt through this resistor RT, so that now this capacitor now starts charging. This capacitor now starts charging. See, now this is why this is started charging. This has started charging because it is providing it is getting a path to go to 4.1 volt. So from 0 it has started charging towards, okay, what is its destination? Its destination is it should go up to 4.1 volt, but it can keep on going up to 4.1 volt. The moment when it is, so now it is keep going here. So now, so let us assume that this is around 2.05 volt. So now when the capacitor is keep increasing from 0 volt, so why the capacitor started increasing? Because you are providing a path for this capacitor to charge towards 4.1 volt. So on its way to, now it is started charging towards this supply voltage, which is 4.1 volt. So now it is keep on charging. So now let us assume that the capacitor voltage is around 1 volt. So this is 1 volt, this is 2.05. So what is output voltage? So now this is, assume that this is 1 volt, this will be still 2.05. So which is more now? 2.05 is more than 1. So that output is still at plus V side. So this condition is still true. So that's why this is at still 4.1 volt. Now we know that this is keep on charging. This is keep on charging. The moment it is slightly greater than 2.05. So assume that the voltage has become 2.05001. So when this has slightly gone above 2.05 volt, so then V minus becomes more than V plus. At this moment, what happens to your output voltage? Because till here, V, this was V plus, this was V minus. So the condition what you had was V plus was greater than V minus. So that's why output was a plus V set. It was a plus V set. At this point, V minus has become greater than V plus at this point. Exactly at that point. Can you see now? It has become more than that. So this will make at this point, V minus is greater than V plus means V naught has to become minus V set. V naught has to become minus V set, meaning this output voltage will change to minus V set. So what is minus V set? So this will become minus 2.74 volt. So when the voltage here from 4.1 has now become minus 2.74. What is this minus 2.74? It is minus V set. It is minus V set. Now the capacitor which was charging towards 4.1 volt now see a voltage which is minus 2.74 as the source voltage. Now naturally what happens? This starts reducing. Okay, now this start reducing. So before that, since the voltage here has become from 4.1 to minus 2.74, the voltage at this point is no more 2.05, it will be minus, okay, what is 2.74 divided by 2? Because V plus now is equal to 2.74 by 2 is minus 1.37. The moment when the output voltage changes from plus V side to minus V side, the voltage here which was there at 2.05, because this was 4.1, will now become half of this minus 2.74, which is minus 1.37. You can see now this automatically comes down to this. So what is this voltage now? This voltage is now minus 1.37 volt. Now what is the capacitor source now? The capacitor source is now on to minus 2.74. Now capacitor started discharging. Now the capacitor started discharging. So now during this time, so this is actually the voltage at inverting terminal. This is the voltage at non-inverting terminal. So this is, we know that this is V plus, this is V minus. So which is more now? See, now this is V minus, this is V plus. So actually V minus is more than V plus. So output, okay, over here V minus is greater than V plus. So that output is at minus V sat. Now it continues to be at minus V sat. So when this is at minus 2.74, the capacitor has started discharging. It is keep on going discharging. It is keep on going discharging. So till where it goes, so its destination is up to minus 2.74. So it will be keep going up to minus 2.74. But whenever the voltage crosses, of course this is 0 volt, when it crosses 0 and it is going still negative, whenever it sees minus 1.37 volt, so now this is keep discharging. When it tries to go below minus, so when this voltage is, assume that it is minus 1.371. So now what is the voltage at the non-inverting terminal? The non-inverting terminal is minus 1.37 volt. What is the voltage at inverting terminal? It is minus 1.371. So at this moment, what is the voltage? So at this moment, V minus is less than V plus, or V plus is more than V minus. So when V plus is more than V minus, what happens to your output voltage? Output voltage will now switch from minus V sat to plus V sat. Minus V sat to plus V sat. So now the moment this switches from, when the output voltage switches from minus V sat to plus V sat, the voltage at this point, which was there at minus 1.37, will go to 2.05, because this has changed from minus 2.74 to 4.1 volt. So this immediately changes to 2.05. So now the capacitor which was going towards minus 2.74, now it changes its direction of charging. Now it again starts charging towards what? The positive voltage 4.1, because this this output voltage has changed from minus 2.74 to 4.1. So now it is keep on charging towards what value? 4.1. But now what is the voltage that it is? It should be compared with 2.05. So whenever it crosses 2.05, the output voltage will switch from plus to minus. This will switch from 2.05 to minus 1.74, and this capacitor start discharging, and when it goes below minus 1.37, again switches. This operation continues forever. I hope you got it. So what we initially started was, we considered this to be ground. Of course, we didn't have this capacitor nor the resistor. When this is at ground, so this was always there at 2.05. The output voltage was supposed to be at plus V sat without any change. Then we connected a capacitor. We assume that let the capacitor voltage be 0. So then that continues to be at so and so at plus V sat. The moment when you connect this RT, now this RT will provide a path for your capacitor. Now capacitor starts charging. This is at the time when you introduce this RT. So capacitor is charging towards this V sat. On its way to V sat, it will come across this voltage, which is nothing but the potential division of this. So whenever it tries to cross 2.05, V, of course, this is nothing but V minus. This is a voltage at V minus. When V minus tries to go above V plus, output will change from plus V sat to minus V sat. So the moment when it changes to minus V sat, this voltage will become minus 1.37 volts, because it's again the potential divider action of minus 2.74. So now capacitor starts discharging. So of course it is discharging or charging towards negative voltage, so which is nothing but discharging. So on its way towards minus 2.74, 0.74, whenever it crosses minus 1.37 volts, then V plus will become more than V minus. So then output will make a transition from minus to plus. So this operation continues. So now the moment you connect this RT to this, so it is keep on charging, discharging, charging, discharging without stopping. So now this once you introduce this resistor to the circuit along with the capacitor with this connection, this will continuously give a square wave of certain on time and certain off time. So this is on time, this is off time. You can see now in this case, this is my square wave because this is my V0. So V0 will going to have an output voltage of plus Vsat peak and minus Vsat as its minimum voltage, and this is my on time and this is the off time. The off time. So now this way we can very simply generate a square wave signal using an operational amplifier. So now you may say that there is a positive feedback as well as negative feedback. Is it an amplifier? No, it's not an amplifier. It's an oscillator. Of course, what do you mean by oscillator? Oscillator is one which changes its state from plus V side to minus, minus V side to plus V side continuously without stop. And it is surprising to see you are not providing any input signal to this. Whatever signal that you are providing is only the supply voltage plus 5 volt and minus 5 volt, and there is no signal that is provided. You are not neither giving the square wave nor giving the sine wave to any part of the circuit. That should be very, very clear. A generator means it generates the waveform by itself. You're not supposed to give any input for that matter. No wave generator are required for giving the input for this. Whatever signal that you get here at V0 pin number 6 is a square wave of amplitude plus Vsat and minus Vsat, and it will going to have certain on time and off time, which we'll find out okay what is the on time and off time. So let me just show you okay how I'm just doing it. So I have rigged up the same circuit. So let me just write the circuit again for you since that is mixed up. So let me write. I'm using a 741 op amp. So this is minus. This is pin number 3. This is pin number 2. This is pin number 3. So this is pin number 7, which is connected to plus 5 volt, and this is pin number 4 connected to minus 5 volt. This is pin number 6. So we are connecting a resistor of 1.5k, 1.5 kilo ohm fixed values. This is again 1.5 kilo ohm. So which we name it as R1, R2. This is my junction, and I'm connecting a capacitor of 0.1 microfarad. So this is the capacitor which is grounded, and I'm connecting a resistor. So here for experiment purpose I'm using a DRB. This is my RT. RT stands for timing resistor. This is my timing capacitor CT. So this is my output voltage V0. So now let us see what is okay, let us first see the waveform and try to find out what is the expression for. Okay, how does suppose if you have made the connection and if you want to see the output will be immediately coming. Of course, it doesn't require any other condition to be satisfied. So as soon as you make the circuit, as soon as you make this connection properly, the output waveform will be coming in non-stop. So this is your output waveform. Having certain on time, that is repeating. Off time also repeats. Okay, here I might have not written this off time same, but it will be the same. And this is having a 0 voltage. This is with respect to time. So this is plus Vsat. This is minus Vsat, and we know that the capacitor voltage. So if you can see here, if you can see my previous thing. So whenever the capacitor voltage reaches this, output will have a transition from plus to minus. Whenever the capacitor voltage reaches this, again it switches from this to minus Vsat to plus Vsat. Since it has already settled down, so let me draw the waveform like this. So let me just, this is my V0, this is my V0. So let me write my capacitor charging discharging. This is an exponential, it will not be a linear one, it will be an exponential charging discharging. You can see this is now exponentially charging and discharging. So this is how it is. So this is my, the capacitor voltage VC, and this is at the inverting terminal. This is at the inverting terminal, that is pin number 2. So what is this voltage? This voltage is plus Vsat into R2 by R1 plus R2. R1 plus R2. This voltage is minus Vsat into R2 by R1 plus R2. This voltage is minus Vsat and this voltage is plus Vsat. And this time, this is my off time. So let me just write this as my T off, because my output voltage is negative, so I'll say it as T off. So this is T on, this is T. So of course the frequency of the signal is nothing but 1 over T on plus T off, 1 over T on plus T off. Now let us see the waveform that we are getting. So what I'm connecting now is, so let me connect a RT of 10 kilo ohm. So this is a 10 kilo ohm resistor. So let me just go back to my circuit. I have already made the connection. So let us try to see the waveform. So this is the waveform what I have. See now I'm using, so let me just go back to my circuit and try to find out okay how I made the connection. So here I'm connecting C1 plus, here I'm connecting C2 plus, meaning I want to observe the waveform at pin number 2, which is my capacitor charging discharging. The voltage at pin number 6 is nothing but output voltage. I'm connecting the second channel. Second channel will indicate the output. The first channel will indicate the capacitor charging discharging. So capacitor charging discharging, that you can see here. See now, I'm already using a supply of plus 5 minus 5. You can see this is plus 5 minus 5. So I have rigged up the circuit. So let me run it now. So this is, I'm already getting some waveform now. The resistor that I'm using RT is now okay, now it is okay 10 kilo ohm. The capacitor value is 0.1 microfarad. If you can see, you can just try to observe some of these parameters. It was said that this voltage is plus Vsat into R2 by R1 plus R2. So in this case, plus Vsat is this, which is your C1 max, C2 max. C2 max is 4.12. So what is half of 4.12? It is 1 point. It is 1 point. Okay, what is, so we are looking at, so I should get 4.12 divided by 2, which should be 2.06. Suppose if I try to measure this voltage, so this voltage which is C1 max should be half of this, and C2 should be half of this. So if I'm using both the resistors of 1.5k 1.5k, of course ideally speaking it should be exactly half of that. You're getting very close to it. So let me write what is Vsat and plus Vsat and minus Vsat. Let me also write what is let me say this is what is plus okay, this is plus VCT and okay, or VCT max and VC min, that is capacitor voltage maximum, capacitor voltage minimum. So capacitor, okay, plus Vsat minus Vsat are 4.10 and minus Vsat is minus 2.74, and the capacitor voltage is one of them is 1.81, the other one is minus 1.5. So these are the values that I'm getting. these are the values that I'm getting. So this, okay, ideally this would have been a 4.1 by 2 and this would have been minus 2.74 by 2, provided if these two 1.5k 1.5k resistors are exactly giving the same values. So because of some practical values, this is not exactly 2.05, this is not exactly minus 1.37 volts. So that's okay. So this is your maximum capacitor voltage, this is minimum capacitor voltage. Now that's what is, this is your maximum capacitor voltage, this is minimum capacitor voltage. You can clearly observe whenever your capacitor voltage tries to go above that, see here. So whenever this is trying to cross this capacitor voltage, that is this voltage, the output makes a transition from plus to minus, see here. So whenever this is trying to go above this, output is going from plus V side to minus V side, exactly this. And on its towards minus V set, whenever it tries to go less than minus 1.5, in this case minus 1.5, it is trying to make a transition from minus V set to plus V set. So that's what is the transition. And you can see this is keep running infinitely. As soon as you start running, so this is non-stoppable. Suppose if even if you make the time period something like this, you can see it is keep running, it's keep running, so it will never stop. It will never stop until you make the supply to go off. Suppose if I just switch off this, then only it goes off, then only it goes off. The moment I just turn on, it just comes up. So it doesn't require any input for that matter. You can see I'm not at all energized the wavegen is not at all used. Now let us try to know why the frequency is 460 kilohertz, why the positive width is 0.8 millisecond, why the negative width is 1.3 millisecond, why the duty cycle is 38%. All those things we're going to see now. We're going to see now. So now let me just connect it. Fine. Okay, now let me just see how do I make this. Okay, fine. So I will, okay, let us try to now get the expression for the pulse width. Now of course while conducting the experiment, you have to choose a certain value of R1, R2 and RT, CT. Try to find out what is the positive T on, T off, the duty cycle and all those stuff. Okay, now let us go to the theory part of it. So maybe we'll discuss the theory part of this in the next video. So in order to conduct the experiment, you have to simply do this connection. So do the connection, connect the circuits as per this. Now you're connecting C1 plus here, C2 plus here, this is going to plus 5, this is minus 5. You are using a DRB. So okay, now okay, you can just have a look at if I change the DRB position. So now let me make this time as something like, okay, a bit lower time. Let me make this. You can see now I'm increasing the value of RT. So when I increase the value of RT, the capacitor will take more time to charge and discharge. You can see now the frequency will reduce, the time periods will increase. Can you see now the time period is increasing? Can you see the frequency has reduced from 400 to 350 hertz? You can see now I'm just keep increasing. So this is I'm increasing the, so okay, why this frequency is not visible is because the entire cycle is not there. Let me make this something like this. Now you can see the frequency is 280 hertz. What I'll do now, I'll reduce the resistance. If I reduce the resistance, naturally the frequency will increase. You can see now I'm reducing the resistance. The widths have reduced. Naturally the frequency has become 2.1 kilohertz, 2.2 kilohertz, or I can even further increase the frequency. Now the frequency has increased to 4.2 kilohertz. I can make it now it is around 6 kilohertz. Now you can see this is around 6 kilohertz now. Okay, this is how the things, of course. Let me just turn on this. This is my capacitor charging, discharging. You can see this is keep. Of course, we have these limitations, so you cannot increase the frequency too much. It's again because of your slew rate issues. So you cannot get very high frequencies using this op amp, which is 741. Suppose if you increase the resistance, sorry, if you reduce the resistance too much, so you'll end up with this type of, so of course now you're not at all getting a square wave. So why you're not getting a square wave is because your op amp takes certain time to respond, to go from plus phasat to minus phasat. Since you are expecting the waveform to be at very high frequency, which is not supported by the op amp that I'm using now. So that's why you cannot get very high frequencies using this op amp in this particular case. So 741 has got a very bad slew rate, which is like, okay, 500 millivolt per microsecond, which is very poor. So that's why you cannot use this 741 for generating very high frequencies. Suppose if you want to have low frequency generation, low frequency is very good. You can able now the frequency is if you can see the frequency is hardly 230 hertz. You are getting it very fine. Suppose if I further increase the resistance, the frequency further reduces. You can see you are getting it very perfect. So you can see the frequency is hardly 50 hertz. Suppose if I make this, now the frequency is so less. So now if you can see what the frequency is hardly 23 hertz. So you can very comfortably get low frequency square wave generation using 741 op amp. But for getting high frequency square wave, it has got limitation because of its slew rate. So that's why you cannot get very high frequency signals. Even frequencies around 5 or 6 kilohertz is an issue with this 741. Suppose if you use a better op amp having good slew rate, you can certainly able to generate high frequency signal. So that's the limitation of this 741 IC, which is having a very poor slew rate. Slew rate of this IC is 500 millivolt per microsecond. 500 millivolt per microsecond. So that is a limitation. That's why I cannot get very high frequency. So now, if I just go for high frequency generation, I have this problem. So now I reduce this. You can see I am not getting very high frequency. So let me just make this somewhere here. You can see now this is also fine. So now you are still at 1.6 kilohertz. If I make the frequency like see now I make this, you can see already started distorting. So this is already started distorting. The frequency is hardly 5 kilohertz. So you might have seen that frequencies of 100 kilohertz, 200 kilohertz, it is highly impossible using 741 because its slew rate is pretty bad. Okay, let us now, for this experiment purpose, so let us try to generate only low frequency signals, and even for low frequency signal we should be in a position to justify whatever frequency that you're getting is matching with your theoretical values, that is, this on time, this off time should be perfectly matched. Okay, we'll just come back to this in the next video. Thank you.